Our project hinges from the fact that when men are diagnosed with prostate cancer, about half of men are told that they have a cancer that might not do them any harm in their lifetime. It's become apparent over the last few years that it's probably best not to treat men who have harmless prostate cancer. In fact, if you do treat men with harmless prostate cancer, you get into a situation where it's hard to show that treating anybody does any good. On the other hand, there's the other half who have a reasonable chance that their prostate cancer will progress and hurt them if it's not treated or, in a reasonably quick period of time. And for them, if they don't know that at the right time, the disease can progress to where it's incurable. They miss the chance to get the proper treatment when they need it. And it turns out I'm a pathologist. I diagnose prostate cancer under the microscope. And I would say it's somewhat our fault that we can't really tell a man with decent accuracy which category he fits into. There's two reasons for that. One is that when we get a biopsy to diagnose cancer, it's a very small thread-like specimen, and we have to look very carefully and try to infer, looking at this tiny sample, what the rest of the prostate looks like, what the rest of the cancer looks like. We get a very small piece of it. And we have to imagine what it looks like in 3 dimensions when we're only looking at it in 2 dimensions. So that brings up 2 different errors. There's one that is the subjectivity of it, the ability of the pathologist to imagine the proper conformation of the cancer. And the other is what we call sampling error. Did the urologist give us the right piece of the cancer, or the radiologist, whoever took the biopsy? We don't do that. Or did they give us a part that really isn't representative? So the big idea we've been looking at in the laboratory is, are there molecular measurements that can be more objective and can reflect the overall state of the tumor in a less spatially confined way? So if you think about if you had a bunch of people and you wanted to tell if they were related, it might be harder to tell by looking at what they look like at any given moment than to actually sequence their DNA and figure out what they have in common. They may be wearing different clothes on one day or a different hairstyle or something. The DNA and the genome gives us a more fundamental view. This grant allowed us to find a certain kind of genetic change that's been understudied up till now, that we think can actually do this. And we were able to develop preliminary data with this funding to show that we can find a difference in this feature called DNA hypermethylation of certain genes in harmless and potentially harmful prostate cancers. And using that data, we were able to obtain a much larger grant from the Prostate Cancer Canada. And that's funding the lab for several more years to look at these genes in more detail and in a much larger patient population. So it's going to be
fantastic news.
Yeah, it's a $5 million grant, and it's shared between 7 different laboratories. We don't get 5 million divided by 7. There are various processes that need to happen, but we're able to support a large number of trainees and to really leverage this into something that we think can make a difference for patients.
I've been in prostate cancer research for quite a while, and all throughout my training. And the picture or our understanding of prostate cancer has really evolved a lot within the past, I'd say, about 5 years or so. And one of the key things that has emerged is that prostate cancer is a lot more complex than we thought it was. So initially we thought it was sequential progression of known mutations that take us from early prostate cancer to the aggressive form. But it turns out that it's a lot more divergent. There's a lot of different paths that early cancer can take to become very advanced disease. And with that complexity, it's very difficult to nail down and say, this is a point where we can interfere to stop this advancement of the cancer. So what our lab has done was we've shifted our focus away from the genomics or genetics of prostate cancer itself, and we focused on the surrounding normal tissue called stroma. And the rationale behind that being basically no matter what happens or what path or route the cancer takes to become very aggressive, the effect that's going to be felt in the neighboring normal cells are going to be consistent. So we found that, we postulated that to be the consistent point that we can look at and predict how the cancer is going to behave. The work is ongoing right now. We've made some very interesting discovery that the stromal cells do indeed behave very differently as the cells become more aggressive, and we're in the process of trying to translate that into clinical application. So that would be sort of in a nutshell what the study's about. And right for that, it's been very beneficial because a novel idea like this that's sort of off the beaten track is very difficult to get funded. And it was a pilot study in design to kind of take us to the next step, and we believe that this has helped us get enough data together to preliminary evidence to apply to something bigger and do a more full investigation, more thoroughly designed study on this issue. Just to explain this a little bit further, it's known that as cancer becomes more advanced, their metabolism changes. So, and that's not surprising because it requires a lot of energy to build up faster, grow faster, and divide faster. But what we're seeing, and there's a couple of other groups that have kind of looked into this in other tumor models, is that the way the cancer cells really interact with its neighboring normal cells is that it sends some kind of signals to those normal cells, and it hijacks or instructs those normal cells, the stromal cells, to alter their metabolism and basically starve them out at the cost of hijacking their metabolic intermediates, gets them to spit them out into the surroundings so the cancer cells can gobble them up and use it for itself. It's called reverse Warburg effect, and it's a very interesting phenomena, and that's something that's just emerging. And we're one of the, I guess, first people really applying it to the prostate cancer scenario.
It's well known that cancer can cause problems with coagulation of blood and lead to clots and even some heart disease. And this is really well known with respect to prostate cancer and the treatment for prostate cancer, including hormonal therapy. So our project was to look at this hypercoagulation of blood with the use of hormonal therapies for prostate cancer. So we're looking at a very sensitive assay to try and determine which men are having problems with this hypercoagulability of their blood, and perhaps target those men for some treatments to save them the complications of having a clot in their leg, or perhaps even a heart attack. So this recent project, we've done some work in the lab looking at these sensitive assays to try and determine who is going to get into trouble with clots. And we also have been following about 50 men before and after they've started therapy for prostate cancer. And we have indeed found a section of about 30% of men who run into trouble with very hypercoagulable or sticky blood. It's a test, so there's two tests in particular. One is called TEG, which really measures how well the blood clots, as well as something called microparticles, which are very small blebs of cells from platelets and from cancer cells, and to try and detect whether or not they lead to hypercoagulable blood. Some of the findings so far, we're actually going back to the bench and looking at cancer cells in the lab to see if by chance, treatments such as chemotherapy or hormone therapy of prostate cancer actually leads to cancer cells leading to more of this hypercoagulation. So we're going down a whole new direction to see if we can actually stop that process in its tracks. Funding from Ride for Dad has been incredible. Funding for these small but important clinical questions is tough from government agencies like CIHR. And these small startup funds for pilots to look at new questions and find some interesting results to go on to get funding and for bigger projects and include more men is, I can't say enough. Ride for Dad's done a lot in our community in terms of advocacy for prostate cancer and prostate cancer research.
So what we're looking at is there's a tremendous amount of information available to men to try and help them make decisions in localized low and intermediate risk prostate cancer about what kind of treatments they want. And in fact, there's a little bit too much information out there. So we're trying to explore ways to take that information and simplify it in ways that men with this disease can understand, so they can incorporate that knowledge and make appropriate treatment decisions that are really based on their individual perceptions of risk and their individual preference for different what we call health state utilities, which are aspects of quality of life after treatment. Ideally, it's incorporated into what we call decision aid modules. So decision aid modules are a way to display information to patients that they would use it themselves, and it would guide them through a decision-making process with the end result being trying to allow them to come to an informed decision about what the best treatment modality is for them, whether that be active surveillance, surgery, or radiation treatments. We would love to see anybody with low or intermediate risk localized prostate cancer. They can either contact my office, and I can put them in contact with Christine Tong, who works at the Cancer Research Institute, and she's our research coordinator for this project. She's the one who takes the patients through all these interviews, and if we either reach out to her or reach out to me, and I will put you in touch with her. We're trying to increase our enrollment through any means we can.